So, good morning. Thank you very much to be here. I am Esteban, project manager of GEOTER company. GEOTER is an engineering company specialized in renewable energies, mainly in geothermal energy, to provide heating, cooling, and domestic hot water for all kinds of buildings, or hot water or cold water for industrial purposes. We have developed many different kind of projects, block of buildings, hospitals, universities, greenhouses, many kind of buildings. So our main office is located in Madrid, in Spain, but we have different offices in Latin America too, in Chile, Mexico, Bolivia, and Argentina. And in GEOTER we cover all the stage of a heating, ventilation, and air conditioning project, since the design, from the design to the execution, the commissioning, and finally the maintenance of the project. And inside of the hybridGEOTABS project, we are focused on the geothermal part, the borehole field exchanger. So, this is the content of my presentation today. I'm going to talk very briefly about the modular schematic of hybridGEOTABS building. Later, I'm going to talk about ground heat exchanger optimization from the design to the operation. And finally, the conclusion. So, as Lieve has talked about it, this is a modular schematic of different GEOTABS buildings in Europe. MPC project is focused. MPC GEOTABS project is focused on medium big installation, medium big buildings, more than 1,000 square meters. And in this kind of buildings, we can find different sources, energy sources, and different emission systems. So, for example, as low temperature system, we can find different kind of ground exchangers. For medium temperature sources, we can find usually heat pumps, water source heat pump, brine source heat pumps, or air source heat pumps. And like heat temperature sources, we have normally gas boilers, thermal panels. For the emission side, the same. Normally, we cover low temperature demand and medium temperature demand with taps, air handling units, or underfloor heating, cooling, and we cover heat temperature demand for domestic hot water or radiators. The objective in the MPC project, searching for the major efficiency of the buildings, is to use geothermal like the energy source and taps like the emission source, searching for the major efficiency, reduce the consumption of energy, reduce cost, and reduce maintenance and improve the control of the whole system. In the part of the geothermal heat exchanger, it's very important the design because of two main reasons. First reason is that the geothermal heat exchanger has an important initial cost, so it's very important the design. It's very important to design a borehole field very optimized, take the major energy exchanger, the major energy that you can from the borehole field, sizing in a good way, and in the other hand, we have to ensure and we have to guarantee that we are going to provide the energy that the building needs during the whole operation, during the life of the building. So it's very important for guarantee, and it's very important for reduce the initial cost, but with a very good operation of the whole system. So, when we talk about the design of a heating, ventilation, air conditioning system in a building, first of all, we have to analyze the envelope of the building, the use of the building, the occupancy, external gains, internal gains, bioclimatic aspects, and finally, we can calculate heating, cooling, domestic hot water, thermal loads. With this information, and thinking about base load, peak load, we can choose which is the best emission system for our building and the best technical design, heating ventilation design for our building. And finally, if we want to cover base load with geothermal energy, we can finally design borehole field for the building. So Peter is going to talk later about geothermal heat pump, but only I wanted to say that geothermal heat pump uses the earth, uses the subsoil like the heat exchanger, and with a very high performance, with a very high rate of performance. Why? Because of the stabilization of the temperature with the depth. This is the typical diagram of geothermal energy. Whenever the season of the year is, at the moment we go deeper in the subsoil, we find the stabilization of the temperature normally at 20-30 meters depth, when we have around 10-15 degrees during the whole year, depending on the area. But we have a stabilization of temperature here, and from this point, if we go deeper, we have around 3 degrees per 100 meters. So imagine at 120 meters depth, we can have around 15-20 degrees during the whole year. So this focus of temperature is very favorable for our heat pump, and this is why the heat pump has a very high CUP and a very high EER for cooling. If we have the building and we want to design the borehole field, first we have to consult the geology and hydrogeology of the area. Okay, we have different maps of the different zones in the different countries, and you can analyze which materials compound the subsoil and if groundwater flow exists or not. With this information, we can estimate a ratio, watts per meter, of energy exchange, and we can estimate in an initial pre-sizing how many meters I have to drill for my installation. But this is not an accurate sizing. This is only a basic information. It's only valid for small installations, like a house, always less than 30 kilowatts. Okay? So, for example, imagine that I have a house here in the west of Madrid, and I consult the geological map, and I can see that I have sand, gravel, clay, and an important groundwater flow. So I can go to this table about the specific heat extraction, and I can see that, for example, gravel, sand, saturated water, I have around 65-80 watts per meter. It's an estimation, it's a rough estimation. So if, for example, if my house needs a 10 kilowatt geothermal heat pump, that means with a CUP of 5, that I am going to obtain 80% of the energy from the ground, and the rest is electricity. So 80% I have to obtain 8 kilowatts from the borehole site. So if I need 8 kilowatts from the borehole site and I have around 80 watts per meter, I need 100 meters, okay, for my geothermal exchanger. But this is only for a very small installation, not for medium, not for big installations. Because when we have an installation more than 30 kilowatts, we always have to do, is very recommended, is completely recommended, is necessary to do a geothermal response test. Geothermal response test is the most frequent, is the most prevalent practice for the sizing of a heat exchanger. So, consists on drill one borehole, a pilot borehole. This pilot borehole is going to be part of the final installation, so it's important. And with this pilot borehole, we can obtain the main parameters of the subsoil, the parameters we need to design our borehole field. These parameters are thermal conductivity, thermal resistance, and ground heat capacity. It's very important to do the test on site because we can analyze the different conditions on site, realistic, not in a laboratory, no? So we can obtain thermal conductivity, thermal resistance, and ground heat capacity. Thermal conductivity describes heat transference along the subsoil. Thermal resistance indicates what should be the thermal lead between the collector circuit and the subsoil for the dissipation of energy. And ground heat capacity is the amount of heat that must be added to 1 unit of volume to increase the temperature. Okay? With these 3 parameters, we can calculate in a good condition our borehole field. The modus operandi of the geothermal response test, the current practice, is first, in the first stage, during 20 minutes period of time, we circulate. Well, first we drill a borehole, no? First we drill a borehole, imagine 120 meters depth. We introduce the geothermal proof, and we fill all the borehole with high conductivity mortar. We wait for 5 days, okay? And we can begin with our geothermal response test. First stage, during 20 minutes, we circulate water inside of the geothermal probe in order to know the unaltered borehole mean temperature, okay? The natural temperature of the borehole. After this first stage, the second stage began. In this case, we began to heat the water which is circulating inside of the borehole during 48 hours. At this moment, we can calculate, because we have 2 sensors at the top of the borehole, one sensor of temperature in the input, one sensor of temperature in the output, and we know how much power is applied. So with this difference of temperature, we can calculate which is the dissipation in the borehole of the energy. And we can obtain thermal conductivity and thermal resistance of the borehole. But we only obtain the average of these values, because we only know output and input, but we don't know what happened in the borehole. We don't know what happened in the different layers of the borehole. We only know the average of these values. So, in this project, GEOTER has developed a new system, an improved system, has improved the system with the enhanced geothermal response test. In this case, what we do is to introduce little sensors inside of the geothermal probe in order to know which is the thermal conductivity at all the levels of the borehole. In this case, the test is something different, because we don't circulate the water inside of the probe. In a first stage, we leave the water during 24 hours in the geothermal probe without movement. And we throw a little sensor which is taking temperature and pressure data along all the borehole, 120 meters depth. In a second stage, we have introduced a linear electrical resistance 120 meters long in all the borehole. So we are going to heat the water which is circulating inside of the water inside of the probe with around 20-30 watts per meter. In all meters, same quantity of energy. And in this case, we don't circulate the water, we only throw sensors during the 48 hours in different times to take information about the different temperature and pressure of the layers of the ground. This is very important because we don't obtain only average values, we obtain the depth temperature profile of the complete borehole. We have information about where are the most efficient part of the probe, of the geothermal probe of the borehole. We can measure the influence of the groundwater. We can locate if we have groundwater flow at the different levels, and we can get information about the regeneration process and the grouting process too. So we have used this system in 6 projects. I'm going to show you 3 of them. All the cases are in Spain. All the test was performed in Spain. and you are going to see the results. No? The first test was carried out during March 2017 in Móstoles. Móstoles is at the south of Madrid, in a borehole 127 meters depth. We introduced a geothermal proof of polyethylene 100 LC with simple U configuration, 40 millimeters diameter. And the area was dominated by arches with ochre shales. And we filled all the borehole with a high conductivity mortar, 2.1 watts per meter Kelvin. Here you can see the result. This is the temperature profile. The first curve here in blue color is the unaltered temperature of the borehole. This is without introduced heat into the ground. So we can see here, if you remember the diagram of the geothermal I showed you before, we can see here at the surface we have around 7 degrees, but at the moment we go deeper and deeper and deeper, we can see that the stabilization of the temperature more or less at 25 meters depth, when we have around 17.5 degrees. And at this moment, we can see the gradient 3 degrees per 100 meters. After this first stage, we began the second stage. During the second exchange, as I told you, we heat the water which is inside of the geothermal proof, around 20 parts per meter. And we can see the different curves during the time. Here we can see the differences of temperature. For example, at 15-20 meters, we can see that we introduce heat, and the heat is storage in the layer. There is not many dissipation here. But here, for example, at 40 meters depth, we have major dissipation, so major thermal conductivity. And at the end of the borehole, 127 meters, dissipation is lower again. So if we translate this information into thermal conductivity, is the black curve in this case, we can see that at 40 meters, conductivity is higher than the rest of the borehole, and the last meters of the borehole are not very efficient. No? So, with this information, if I introduce this information in a borehole sizing software, we can obtain major results, and we can size better our borehole field. These are some pictures of the process. This is me. And the second test is in Madrid-Barajas Airport. In Madrid-Barajas Airport, during January 2018, again in a borehole 127 meters depth with a geothermal proof, again polyethylene 100 simple U configuration for 40 millimeters. In this case, the area was dominated by greenish and brown clays, locally micaceous sands, carbonate and flint levels. And we fill the borehole again with a high conductivity mortar. In this case, you can see here the depth of the borehole, here temperature of the borehole. And the same, we can see here the unaltered temperature of the borehole. We can see in a very easy way that we have here the stabilization of temperature only at 10 meters depth, and since this point we have an increasing of temperature, a natural increasing of temperature, a gradient of 3 degrees per 100 meters. We begin the second stage, and you can see here the differences. There are not many differences in this case, if you see. Thermal conductivity is lower here, no? Because dissipation is lower. Thermal conductivity is something major here, and at the end of the borehole is lower, but it's very similar during the whole borehole, no? So you can see here thermal conductivity is very similar. The efficiency of the different parts of the borehole are very similar. And this is the borehole resistance in the same way. These are some pictures of the process. And this is the most important test. In this case, you can see huge differences. This enhanced geothermal test was carried out in Asturias at the north of Spain in a borehole 127 meters depth and the same configuration, polyethylene 100, simple U configuration and high conductivity mortar. In this case, the area was dominated by limestone, loams, clays and sandstone. And in this case, you can see that the difference is huge, completely huge. We can see in red color the unaltered temperature of the borehole. Here is not so clear than in the other cases, but we can see that more or less the stabilization of temperature is around 20-25 meters depth. And we can see more or less a gradient of 3 degrees per 100 meters. That is why, because there is a very huge groundwater flow in the borehole, as you can see here. At the moment we begin to heat the water, which is inside of the geothermal proof, we can see the differences. We can see that here the dissipation is maximum. Because we introduce heat into the water and it's completely so in the different point here we can see the dissipation is very low. Here we can see that, for example, we have a little groundwater flow too, and we can see now the results about thermal conductivity. As you can see here, from 50 to 90 meters depth, when the dissipation is maximum, we can see that the results are completely high. So this information is very useful for the simulation, for the geothermal simulation. Because if we introduce this data, the program, the software is going to tell us how many meters of the borehole is the most efficiency possibility. No? So I am going to begin to talk now about the borehole field simulation. In this case, I used EED, Earth Energy Designer software. Is one of the most popular softwares about geothermal sizing. And in the first stage, we have to introduce here the parameters of the subsoil. We have to introduce thermal conductivity, thermal capacity, the temperature, the ground surface temperature of the area, and we have to introduce the geothermal flux in this area. In a second stage, you have to introduce different features about your geothermal installation. You have to choose if you are going to use simple U, double U configuration or a coaxial geothermal proof, for example. You have to introduce the thermal conductivity of the mortar. Here you can introduce the delta T of the geothermal heat pump at the evaporator side. And here you can introduce a little pre-sizing of your installation. Okay? In a third stage, we have to introduce here the thermal loads of the building, heating, cooling, and domestic hot water. And we can introduce the CUP and the EER at the conditions that we have in the building. For example, if we are going to operate with taps, we have to introduce CUP at 25 degrees for heating, for example. 28 degrees for heating. So we have to introduce the COP, taking into account the output temperature of our emission system. Here we introduce during the different months of the year, which is the thermal load, heating, cooling, and domestic hot water. And finally here we introduce power peaks for heating and for cooling. This is, for example, this is an example about one real building. They have the thermal loads, January, February, March. So this is the information I have to introduce in the software. But only the energy that the geothermal borehole field is going to cover, only the base load. I have to calculate base load, and this is the information I have to introduce in the software. Finally, I have to establish the temperature limits of my borehole site. Usually, temperature limits are plus minus 17 degrees, taking as reference the another temperature of the borehole, plus minus 17 degrees. For example, if the another temperature of my borehole is 14 degrees, the maximum temperature that I have to introduce in the software, that the maximum temperature of the heat fluid has to be 14 plus 17 degrees, 31. And the same for heating. This is the borehole side. This is the water of the which is circulating inside of the geothermal probe. And the minimum temperature is 14 minus 17 degrees, minus 3 degrees. This is because performance, this is because of we want to guarantee the performance of the heat pump, of the geothermal heat pump, but it's because environmental issues too and regulations, and in each country you can find differences. Okay, but this is the standard regulation. And here you can see which is the medium temperature of the borehole during 25 years. You have to choose an horizon of operating, usually 25 or 50 years. In this case, 25 years. And we can see which is the minimum temperature in the borehole during 25 years. And this is the maximum temperature in boreholes during 25 years. And we have to guarantee that we are not to reach 31 and minus 3 degrees. And in this case, this is during the year 25. This is the changes in the temperature of the water which is circulating inside of the geothermal probe. So in this case, if you see, you can see here a stabilization of temperature. So this simulation is okay. In this case, taking into account the three previous tests, I have taken into account three different scenarios. First scenario is engineering calculation. It's only with my experience with the materials, which compounds the subsoil. I estimate that thermal conductivity is around 1.95. I am not sure, so I introduce usually a security factor for the calculation. In this case, I have performed a geothermal response test, so I know the average thermal conductivity in the borehole, 2.009. And in this case, I know the complete profile of the borehole. I introduce this information in the software, and the software give me the best configuration. With this best configuration, I can reach a thermal conductivity, choosing the different levels of the borehole, of 2.192. So this in the three cases, Móstoles, Barajas, and Gijón, and we can see the differences, for example, of Gijón here. We can see that if we size the borehole field only with engineering knowledge, with geothermal response test knowledge and with enhanced geothermal response knowledge, we have checked that we have a reduction of 11% performing a GRT, and we have a reduction of around 14-21% meters to drill performing an enhanced geothermal response test. So with the enhanced geothermal response test, we can reduce the meters to drill, only improving the design of the borefield. So we reduce the cost, the initial cost, which is very important. And the cost to perform a geothermal response test and the cost of an enhanced geothermal response test is the same, because the devices are very similar and the price is the same of the product and the price of do the test, or perform the test. And this is the three cases: borefield and cost analysis. This is only for the design part. Now I'm going to talk about the operation phase, because during the operation phase is very important to know the behavior of the ground through the continuous monitoring of the borehole is very important, because different reasons. We can control the changes of the thermal conductivity during the years or during the seasons, because you can find changes during the year because the groundwater. You can change which is the differences if I have groundwater or if I'm not groundwater. I can study better the overloading process and the regeneration process of the borefield, and I can predict with the MPC, with the mobile predictive control, I can predict what are going to happen in the borehole during next months. Or, for example, like we are talking about hybrid GEOTABS buildings, we can decide, taking into account which is the state of the borehole site, we can choose which is the energy source I want to use. Maybe it's interesting for me to use the geothermal heat pump or not, the air source heat pump, because the different condition of the temperature of the earth, or because the demand of the building changes, because the use of the building changes. So I need to know information, continuous operation about the heat exchanger during the operation of the building. Only introducing a fiber cable into the borehole, I can see this information. A fiber cable costs 2,000 euros, 3,000 euros. It's not very much. And finally, we can control, and this is very important overall in climates like south of Europe, in Spain, Portugal, Italy, Greece. The most important is the thermal storage. In these countries, cooling loads are completely very important, so we can take energy of the ground during the winter and we can dissipate energy during the summer. And we can search the equilibrium, we can search the balance into the ground to have the best conditions during the summer and during the winter. So finally, only to say that, for example, this is a real simulation of a building, but this is a reality later. So it's very important to see the differences between the simulation, the first simulation, and the real use of the building, So we have to be able to respond until these changes. Okay, and the conclusion is that with this system, with the enhanced geothermal response test, and with the control of the operation phase, we have many data, and we can use this data to improve the sizing of the borehole or the operation of the borehole. which is very important because it's a key module of a hybrid GEOTABS building, and it's very important to reduce the cost and reduce the energy that we are going to use in the building. Okay? Now Peter is going to talk about geothermal heat pumps.